It is a pleasure and great honor for me to introduce today's speaker, Paul Scheier from Innsbruck University. Paul Scheier is a professor at the Institute of Ion Physics and Angewandte Physik and chair of the Center of Excellence in Ion Plasma and Applied Physics in Innsbruck. Paul got his PhD with Tilman Merck in 1988, and after this he actually continued with his research in Innsbruck, but he also has his experience as a high school teacher and from work in a private company, which is maybe not so usual among us. After this he continued, and between 1997 and 2000 he was visiting researcher at the University of Hawaii, and you will see from his dressing today that this gave some impression on him. And he was then working with Carl Sattler on electrical properties of silicon clusters, and at Gießen University later on working with electron impact ionization of fullerene ions together with Erhard Salzbohm. He has further made many research visits, shorter ones, working on photon, electron, and heavy particle interactions with various types of clusters, biomolecules, and surfaces. And he's thus covering many Icpeac fields and all of its projectiles, the photons, the electrons, and the ions. He's very actively involved in several European networks dealing with electron-molecule collisions, radiation damage, and the physics of droplets. And he has, for example, made many important contributions to the understanding on how even very low-energy electrons may damage biological molecules. Since a number of years, he is focusing part of his research on helium nanodroplets, and that's the topic of today. So I would very much like to welcome Paul Scheier on stage to talk about cold collisions inside helium nanodroplets, chemistry close to 0 Kelvin. Please, Paul.
Thank you very much, Henrik, for these kind words. And thanks to the organizers, particularly the board, selecting me as a plenary speaker for the Icpeac conference. It's in fact my 9th Icpeac conference, and the first one was the one that has been already mentioned by our local chair, the Brighton Icpeac in '87. I also am deeply impressed by how the local organizers managed to bring so many young students. So this is really unusual and a great effort from them that they put so much support to the students, and this is now reflected in the audience where I see so many young scientists. This is really great, and this is making this conference very young and very lively. Now, talking about young scientists, I want to thank my group. Here is a current picture taken a few weeks back in Innsbruck. Unfortunately, due to the vacation season, the people on the lower were missing, so they are only here as a picture added. And particularly the guys here, Johannes Postler, Martina Harnisch, Andreas Maurer, he is not here, but Stefan Ralser, he is here, and Michael Renzler, they contributed very much to the work that I can show today. The people on the left side, they are former students and postdocs working with me in the field of helium droplets, and there I want to mention particularly Peter Bartel and Matthias Daxner, who contributed most to the topic I covered today. The people on the right side of the screen, with the blue frames or blue underlaid colors, these are experimentalists who collaborate frequently with us. On top, it is Diethard Bohme from York University in Toronto. Then it's Olaf Echt from Durham, New Hampshire, Peter Tönnies from Göttingen, Andrew Ellis from Leicester, and Eugen Illenberger from Berlin. On the theoretical side, we enjoyed a collaboration even with the local hosts. So Fernando Martin, Manuel Alcami, and their postdoc Yang Wang, they published a very fine paper with us together on fullerenes that had a few helium atoms adsorbed. And in collaboration also with Henning Zettergren, he also was part of that paper. We have a recent collaboration with Robert Zillich from Linz And in-house, we have support from Michael Probst at the bottom of this slide. Financial support is very important and should be mentioned, and most of our financial funding is provided by the Austrian and Tyrolean Science Foundation, as well as the Austrian Academy of Sciences and a little bit the European Commission in Brussels. Probably I'm too far away. Okay. So this is the outline of my talk. It will be a quite extensive introduction into the field of helium droplets. I start with helium alone. There are a few facts people probably may know, others are quite unknown. A little bit about helium nanodroplets, how we can make them, what are their properties, how we can dope them, some applications, some recent ones like quantum vortices and nanoparticles being formed inside helium nanodroplets. That will be covered in the first part of the introduction. Then it will be about ionization, how we generate charged species from helium nanodroplets, pristine and doped with foreign species like molecules or clusters. There will be cations and metastable helium playing an important role, and by heavily ionizing them, shooting intense laser fields on helium nanodroplets, kind of an ultra-cold plasma has been formed, and that's a similar thing that we also discovered in our helium droplets when we do it with electrons. And then there will be the main part of my talk. This is about helium anions, negatively charged helium, which at first sounds quite strange, but it's an electronically excited helium which can capture quite nicely a second electron. So it's a helium plus, basically, which is carrying two charges, two loosely bound electrons. Then there will be two reactions as examples, how helium minus can drive interesting chemistry and physics inside helium nanodroplets, and then a short conclusion. So some facts about helium. Helium was discovered in 1868 in the chromosphere of the sun during a solar eclipse in India by a French astronomer. And he saw this very pronounced, strong yellow line that he couldn't assign, and others said, well, that's not possible that there are other elements in the sun than on the Earth. So it took some time until people realized that this is indeed a new element. It was a few years later discovered in some minerals and in natural gas, and by extracting a lot of them, they could measure its mass, and they figured out that it's indeed a new element. And due to the Greek name Helios for sun, they gave it the name helium. Helium is the second most abundant element in space. It makes about 24% in mass of the visible matter. And in the Earth, it is quite rare. The Earth's atmosphere is too warm, and the gravitational force of the Earth is not strong enough, so it escapes gradually into space, which gives a density or a concentration of only 5.2 parts per million in the atmosphere. Helium is extracted mainly from natural gas. These are the sources where it's collected. And there are natural sources in the past that had 12% helium. At the moment, the top sources have 7% of the natural gas helium. Helium has a very high heat conductivity and a really high speed of sound, about 3 times larger than air, which gives this funny Mickey Mouse voice when you inhale it. So I think everybody knows the helium voice. It's often part of movies, and I think everybody who works with helium in the lab tried it out. And if not, do it, it's fun. So this is due to the speed of sound, so 3 times faster, that gives this high pitch. The pressure and phase diagram shows, the phase diagram shows that helium can only be solid when it's pressurized beyond 25 bar, which is unusual. Even at 0 Kelvin, it remains liquid when the pressure is lower than that. And some other novel aspect was observed. The liquid makes a phase transition at 2.16 Kelvin, which is called the lambda line, due to the shape of this curve, where the transition from a normal liquid to a superfluid happens. And superfluid means that helium has no friction, no internal friction. And here it's a transition in this BBC movie from normal liquid to superfluid, and you see that on the container on the bottom, the superfluid helium managed to creep out even to tiny fissures where even normal liquid helium cannot escape. So it's very tricky to make containers that are really tight for helium superfluid. Applications for helium are quite plentiful. For instance, ballooning, or in blimps it's used for flying. It is used in scuba diving or in intense care. When you mix helium with oxygen, it's much easier to breathe. So for intense care patients, this is a very common help for breathing. It supports them. Its main applications is cooling of superconducting magnets. That's about 32%. And the others is pressurizing, purging, and welding. That's about 50% in total. And some other example where helium is used, which is, well, except for leak detection in our labs, this is rocketry. When you have a rocket with a liquid fuel, such as the Saturn V, when the pumps are dragging out the fuel, the empty fuel container would collapse. So there's a vacuum being formed, and the pump is working against some vacuum. And in order to prevent this, the fuel was replaced on the top with helium. And for one launch of a Saturn V, 370,000 cubic meters of helium were required. Now helium nanodroplets, they are formed whenever you have a nanometer-sized piece of helium, of bulk helium in vacuum. It vaporizes from the surface and cools by evaporative cooling to a temperature of 370 millikelvin. That's an isothermal temperature which it reaches similar to the ice-water mixture, and it stays there basically forever. And it's interesting that once you form these helium nanodroplets, that they are pretty stable, because helium doesn't absorb in the visible or even from the infrared to the VUV. The first excitation level is 19.8 eV, which is in the extreme UV already. And so black body radiation is not warming them up. So you can pass a superfluid helium droplet through an oven, which is at a temperature of a few, even 1,000, let's say 1,500 centigrade, and it doesn't heat up by radiation. Helium can pick up easily species, foreign species like atoms or molecules, and if they are closed shell systems, they go to the center, so they form a cluster in the center. But if they are open shell structures, such as alkali metals or hydrogen atoms, they are located and trapped on the surface in some dimple sites. The ones that go inside we call heliophilic, and the ones that are outside, they are called heliophobic. It's a very efficient cooling agent, and the speed of cooling is 10 to the 10 Kelvin per second. So whenever a dopant hits the droplet, it quickly thermalizes, and by evaporative cooling, the whole system reaches again the temperature of 370 millikelvin. That makes them very nice nanoreactors at very low temperatures. So molecules that are picked up quickly in their low vibrational ground state. The formation of helium nanodroplets is made by a supersonic expansion, like many of us are using for forming other clusters. But in order to achieve helium droplets, we have to be at very low temperatures. So when we use 20 bar pressure at the cluster source before the nozzle, we need to have temperatures between 10 and 20 Kelvin. And in this regime, the helium still remains gaseous before the expansion, so it's a normal condensation like we do it with other clusters typically. The average cluster size that is resulting from such an expansion is in the order of a few hundred to 10 to the 4. So they are rather small droplets. When we go lower in temperature, below 10 Kelvin, there's a phase transition before the expansion, and the helium becomes liquid. So we pass a pressurized liquid through a 5 micrometer nozzle into vacuum, and then the cluster size increases up to about 10 to 100 millions. And then when we go even lower in temperature, we can manage that during the passage through the nozzle, the helium becomes superfluid, and then we have really large droplet sizes in the range of up to 10 to the 13. These are already micrometer-sized objects. But whatever we are doing, we end up with a broad distribution. We never can make clusters on one size. This is the dream of all cluster experiments, to have monodispersed clusters. This is a log-normal distribution, and most of these expansions are ending up in this kind of distribution. This is the average size of 1 million, and about 15% of the particles are smaller than 3 times this average size, and about 15% are about 3 times larger. So keep in mind that this is always a very broad distribution that we are working with. It makes it a little bit worse even when we do pickup, because the cross-section for pickup is depending very much on the geometric cross-section of the particle, which is the number of particles to the power 2/3. And when we add this into this curve, we see that particularly the big droplets are picking up a lot, and it's very difficult to achieve conditions where you have a specific number, let's say only 1 molecule inside. This is sometimes very important, so often you end up with 0, and only a few have 1, in order to be sure that you never have 2. The shape of nanoparticles, of these nanodroplets, they could be measured with X-ray diffraction. Just recently, by the group of Andrei Vilesov at the LCLS light source, a free electron laser in Stanford, they imaged a single droplet by X-ray diffraction, and they figured out that some of them are indeed spherical, some are elliptical, and a few are even like Italian cheese or a Swiss cheese, almost like a wheel. Now, in order to achieve such shapes, it's clear that these particles have to have a lot of angular momentum. And this angular momentum is conserved. Once you put in angular momentum into superfluid, it remains. There is no energy dissipation. Now, the angular momentum is probably provided by passing the liquid through the nozzle. And these nozzles are made mechanically drilled. So 5 micrometers drilling mechanically. It's a company in Germany that does it for all the world, and somehow they do it. And it's probably similar to a bullet going through the barrel of a gun, which is typically also some drilling in it to give some angular momentum on purpose to make a stable trajectory of the bullet. In this case, it's an effect that is simply there, and it ends up in these funny shapes. Now, if you dope these droplets, these are very big ones, 10 to the 13, and dope them with xenon, then the xenon somehow is trapped at particular spaces inside. And these are quantum vortices. So whenever you have angular momentum, like when you stir your coffee mug with a spoon, you start to form a vortex. But unlike in a normal liquid where energy is dissipated and the vortex dies out quite quickly by friction, here it doesn't happen. It is preserved forever. And these quantum vortices go completely through, so, it's the wrong pointer. They go through from the one side to the other, so all across the nanodroplet. And they always are terminated at right angles on the surface. And apparently these quantum vortices are more attractive to the xenon, so the xenon is located there, and its X-ray response is much stronger than the one of helium, and so you can see it in the X-ray diffraction like as these speckles here. And from the number of these speckles they observed, they could determine that the density of quantum vortices is 100,000 times higher per volume in comparison to the bulk superfluid. So a lot of angular momentum is provided to the particles when they go through the nozzle. 2 years earlier, the same group managed to pick up silver atoms into these heavy droplets. And again, the dopants were preferentially sitting down in these quantum vortices, forming nanowires going all through the nanodroplet, so having a length of micrometer and a width of only a few nanometers. And they soft landed them on a transmission electron microscope grid. This is amorphous carbon. And these droplets that fly with only 200 meters per second provide a perfect cushion. So when these wires were landed, it's indeed a soft landing. They do not change, and not much energy is given to the gold wires. All the energy is dissipated by this huge excess of helium. Similar experiments were done a little bit later by the group of Wolfgang Ernst in Graz, and they did X-ray diffraction with very high resolution, and they figured out that nanoparticles that are also formed here of gold and silver in these helium droplets have nice crystalline structures. And it is here a dodecahedral structure, an icosahedral structure, and they also found out FCC. And the funny thing is that the FCC structure is by far the smallest. But all these experiments suffer from one big drawback. They generate and soft land the thing in ultra-high vacuum, but they transfer the sample through ambient air at ambient temperatures to the transmission electron microscope. So presumably annealing could have changed here somehow the crystalline structure of these nanoparticles. Another example how nanodroplets can be used for future nanotechnology was shown here in this work by Andrew Ellis and his colleagues. They made core shell nanoparticles. So it's a nickel inside, a little nickel core, and you see it's still at the XPS, and it's surrounded with a layer of gold, and thereby they could prevent oxidation. So it passivates this nanoparticle, and you can make nice nano dots that are probably stable under ambient conditions by using the right amount of the two metals. It has to be a quite thick layer of gold, however. And in Graz, they even extended this to nanowires. This is a core shell nanowire, in the center a gold layer, and outside a silver mantle. So large nanodroplets and the size distribution of these nanodroplets have to be measured. Why do we know that they are log normal? Well, these are experiments that have been done already in 92, and later on in an improved version by that group in Göttingen in 98. And here it's a retarding field analysis, and here it's a simple deflection method. The basic idea behind these measurements is the following. All particles from a supersonic expansion have exactly the same speed. So mv square, when v is a constant, is actually the mass is equal to the kinetic energy. So the kinetic energy is exactly a measure for the size of the droplet, and with these filters, as well as with the retarding field, we are just measuring kinetic energy. So this is a very simple way to measure the size distributions, and you see it's a perfect log normal distribution here at average size of 9 million, measured with anions, so negatively charged droplets. There's a little feature at the low mass size. This is about 250,000, 200,000, where they have here a funny structure which they assigned to a bimodal distribution of the neutron. I probably can convince you towards the end of my talk that this is something different, the reason for this second hump. So by some other motivation, we also started to measure size distributions of nanoparticles. It was not the real idea and the real aim of the work, but nevertheless, this was our experimental approach. Instead of a simple deflector pair, we used a cylindrical energy filter, and with this, we could measure very nicely log normal distributions. This was measured here at very low current. When we increase the current to about 10 times more, suddenly we have a distribution which changes. The big clusters are relatively decreased, and at low masses, a nice hump, like it has been observed by the Göttingen group, is appearing. Increasing the current more, this funny peak down here at about 250,000 increases, and at very high current, we changed the log normal distribution to a very narrow Gaussian distribution. And the intensity increased by a factor more than 1,000, and in the meantime, we could achieve yields of about 1 million counts per second, 1 million droplets per second, all having the same size, 250,000 plus minus 2,000. So this is an interesting process going on, which transfers huge, broad distributed clusters all into the same size. And it's clear that it has to be something like a Coulomb explosion. So we multiply charge our droplets. This is due to the fact that we can hit each droplet with more electrons, and somehow they rip apart into singly charged units, yielding all the same size. So there are two possibilities, either some fission, symmetric or asymmetric, or probably a Taylor cone, similar as in electrospray, where highly charged droplets are spitting out always uniformly sized little droplets, as nicely measured experimentally by Thomas Leisner and Bernd Huber here in the audience. So I bet that it is something like a Taylor cone which is responsible for these singly charged species that have this uniform size. So this is still 250,000, and when we add it up, you see that the broad distribution changes here to a very narrow Gaussian distribution, and with the energy filter, we select only the narrowest, highest part of it. So these would be interesting objects for further studies. So doing pickup with these mass-selected helium droplets could provide more mass-determined and more well-defined nanoparticles as well. So this is the next step that we are going to do. Now when we ionize helium droplets and we look at little ions with our normal mass spectrometer instruments, we see that there are little clusters, each of them representing one helium cluster from 1 to here about 30. And with the quadrupole instrument, they managed here to see some magic numbers. The 4 is particularly magic when the cluster is really high. Bernd von Issendorf did this in collaboration with the Göttingen group, and they had a nice explanation that 2 metastable excimers on the surface come together and form this helium-4+. But here the 7, the 10, the 14, they are always there as magic numbers, but it's a little bit questionable for the 7, because in all our instruments we have typically nitrogen as an impurity, which is also at mass 28. So let's see if that's really helium or if it's nitrogen impurity. With argon-doped clusters, we see that most of the ions are bare of helium. A few contain a little bit of helium attached, but this is one of the first measurements for doped helium droplets being electron ionized. Now, our experiment with high resolution, it really shows there is helium-7 and there is also nitrogen, but we can separate the two, although both have 28 nucleons, but this one is more heavy, and this is indeed helium-7 on the maximum. When we ionize a doped helium cluster, there are different mechanisms. The chance that our electron hits the dopant, which is tiny in comparison to the size of the helium droplet, it's basically 0. But it will more likely interact with all the helium that is surrounding it. So we can either generate metastable helium or we can make helium+. These are the most important channels. And helium metastable has enough energy to basically panning ionize everything except neon, and helium+ can charge exchange with everything. So this is probably the most likely channel for high energy. Here visualized in this animation, we hit somewhere a helium, we make helium+, and by resonant hole hopping, the charge is migrating towards the dopant in the center and transfers its charge. So it's capturing an electron, and then the dopant is ionized. Now, in this case of a fullerene, as indicated here, the ionization energy of helium is 24.6, whereas the ionization energy of a C60 is only 7.6, and all the difference in energy is going into the dopant. So the dopant is highly excited, and at the same time, we have this enormous cooling power of helium. So it's a quite interesting fight between heating up the dopant and cooling it back down. For low energy, we can form electron bubbles. They have been identified already in bulk helium. This is due to Pauli repulsion. When you put a low energy electron into helium, it pushes away the 1s electrons from the helium, and it forms a bubble which has a size of about 17 angstrom in diameter. So it's a huge vacuum void which is made by this charge, and on the long range there is attraction, and it makes a very heavy, very immobile object in our droplets. One point which is quite intriguing and was never answered so far properly in all the papers that were done about helium droplets is how are actually the ions escaping from the helium. All cations that we form are strongly heliophilic. If you put the ions into solid or liquid helium, then it will form an Atkins snowball. The charge is polarizing the surrounding helium, and it binds it quite strongly. So we have a few layers, at least one layer of helium, which is solid, covering the ion. And so the preferential position of these cations should be in the center or somewhere inside the helium. But in our experiments, most of the times, we observe that the ions are ejected or pushed out of the helium without any helium attached. So where is all the energy going and how can this happen? For little clusters, for little droplets, we can vaporize everything, no problem. The binding energy of helium is about 0.6 millieV. This means when you deposit 1 eV energy into your system, you can vaporize 1600 helium atoms. But for a cluster of a few million in size, the energy that is required for vaporizing this droplet completely, it's kilo eV, and this we do not have. So there is a strange thing going on which people cannot explain at the moment, and you will get an answer during my talk to this. Let's look at our helium clusters. Pure helium droplets ionized by electron impact. It's a nice exponential decrease. This is logarithmic scale, linear here, and so it goes down first almost exponentially, then the slope changes a little bit, the slope changes even more. And when we zoom out into the longer mass range, we see that this continues, and we have here helium, helium all over to 50,000. Unfortunately, the instrument cannot measure heavier ions, but you see that even in the range of 16,000, we have here 4 mass unit separation of peaks, so it's clearly helium clusters. So there are heavy helium clusters being formed, and from the other experiment that I showed with the retarding field or the energy selector, we know that there are even very heavy ones like 10 million, 100 million helium atoms. So somehow these little ions have to be pushed out, and one way to do that is Coulomb explosion, asymmetric Coulomb explosion. Whenever you have one charge already sitting in a helium droplet and you ionize it a second time, the two cations will repel each other, and due to exceeding the critical Landau velocity, which is the maximum speed of no friction, you will have friction and you will not form clusters, and you can kick out ions, even the helium plus, from the large droplets. That's the explanation for these low mass ions being observed. This is our experimental setup. From the outside, let's take away the vacuum vessel. We have here a cryocooler, closed cycle cryocooler with a power of 1.5 watt at the 4 Kelvin stage. And in order to decouple vibrations to the cluster source, we connect them with copper braids at the moment, both here the cold stage and the warm stage at 40 Kelvin. The helium line is pre-cleaned here with at very low temperature going through some molecular sieve. So we have a purity of probably 8.0, and then the helium passes here at 20 bar, typically through our 5 micrometer sized nozzle into vacuum. Thereby, droplets at around 1 million average size are formed, and let's fly now with one of these droplets through the instrument. We have here a skimmer which is doing differential pumping, and now we go through in this next differentially pumped stage where we have a pickup cell, let's say C60 is incorporated. It's very hot because it comes from a hot oven, and evaporation of helium, evaporative cooling is bringing it down to the temperature of the droplet. Then we have a second pickup cell, so we can make nice complexes of fullerenes and something else, for instance. And then we fly with 200 meters per second to the electron ion source. And here we intersect our doped helium droplets now with electrons, and by Coulomb explosion and by some very probably heavy ionization, these ions are then simply kicked out, and we analyze them now with our time-of-flight instrument. This is an orthogonal time-of-flight machine. So we have here a continuous formation of helium droplets, continuous ionization source, and then we feed in here constantly ions into this extraction region. We put in a short extraction pulse for microseconds, which is kicking out the ions, and then we analyze the ions for about 100 microseconds. And in the time that we wait until all this mass spectra has been taken, we feed in new ions into the extraction region. And doing so, we achieve very high duty cycle. In this machine, for heavy ions, the duty cycle can go up as 90%. So it's very, very efficient to measure. It gives us very good signal-to-noise ratio. The machine is all computer controlled, except for opening gas cylinders. You have to go into the lab, but you can move and do everything remotely via a computer from home, for instance. And that's also why measurements are done all over the weekend. And you see that students actually like times like 2 o'clock or 3 o'clock in the morning. Apparently, when they came home from some night out, they look at the machine and see, I can do something new. So it's really efficiently used. So that's if everything would work well, I could run an experiment here, but the connection is not fine enough, so I don't try it. Now let's look for the ionization of helium, the dimer. This dimer is the most peculiar thing. The potential energy curve actually has a minimum at around 3 angstrom, but the wave function of the dimer is spread out over more than 100 angstrom. The most probable distance to find the dimer is around 52 angstrom. So it's a very, very delocalized system. And when we ionize this very weakly bound dimer, we have to do it vertically, going up here vertically, and we can ionize it only here in this asymptotic range. So basically, we need 24.6 eV in order to make a cation. However, there is one possibility going via electronically excited states. This 1s3p state, this is high enough in energy, and it's also attractive because we remove an antibonding electron. We can have autoionization, and this channel indeed is accessible to form dimers or clusters at energies that are way lower than the ionization energy of helium+. This has been confirmed experimentally at the synchrotron by the Göttingen group together with Bessie. They saw here these 3p, 4, and 5p states that really form clusters, but not monomers. In the monomer, this channel is not available. A little bit later, well, a few years later, measurements were done in a more advanced light source. This is Elettra in Trieste. And here, people measured cations for pure helium clusters with a little bit of water impurity in the machine. They saw the dimer as expected, but they also saw here a tiny little bit of a monomer. So apparently there is a new mechanism that can form a monomer cation at energies way lower than where we would expect to have it. And the reason or the explanation is that it's two metastable helium that come together, and in some they have almost 40 eV, so this is enough for autoionization then. With electrons, we see exactly the same. So also with electrons at 23 eV, we see a little bit of helium+. When you use even a free electron laser with much more power and bigger droplets, before it was about 2,000 average size, here it's 50,000, they start to see a cold plasma. So they start to excite so many helium atoms that the whole droplet gets highly ionized. And the electrons that typically should have here an energy around 16, 17, 18 eV cannot escape anymore because the Coulomb repulsion or the Coulomb attraction of the highly charged droplet is keeping them back. And that's why the photoelectron distribution peaks up here at 0. So this is an indication of a really highly charged droplet being formed by this intense laser, and they call it a super cold or ultra cold plasma. With electrons, you can do basically the same, but it's manifested a little bit differently. You cannot measure photoelectrons, but you see that helium plus and helium-2 plus are being ionized at 21 eV already in a kind of resonant-like structure, whereas helium at 300 Kelvin is ionized only at 25 eV roughly, as expected. The explanation given by the Göttingen group at that time was somehow making a helium metastable responsible for it, but you see that they were not very sure about the helium plus, so they put it here in brackets. For a dimer, one could expect something that works, but for the helium plus, this is certainly not working. We remeasured this, and we did a current dependence of this effect. We have here a helium plus ion efficiency curve, and we would expect the threshold here at 25 roughly eV. And we see a nice resonant structure at 22. For the helium-2, there is a nice hump still there, and for bigger clusters, it's gone. So this is ionization as we would expect. This is the ionization threshold for helium. When we reduce the current, you see that the all structure in this low energy range is very much suppressed. It's still there, but it's much more going down than this part here. And this nonlinear effect, the nonlinear dependence on the current indicates already that it is a 2-electron process at most, probably even 3 or more electrons are required for this channel. And the final answer to it is helium minus. And this is now the main part of my talk that you will see in the next 15 minutes or so. Helium minus has been discovered actually already in 1939, mass spectrometrically. Helium plus was passed through some collision cell, and by electron transfer, capture of electrons from the collision partner, helium minus was formed, and apparently its lifetime is long enough that you can measure it in a mass spectrometer. Also, the helium-2 plus was formed in a similar way a few years later by an American group, and also that was done by passing helium-2 plus through a collision cell. The lifetimes of these anions were measured at the storage ring in Aarhus, and later on by the group of Henning Schmidt and Henrik Cederquist, my chair, and it was published in PRL, but as well in a proceeding of the Icpeac, of the Belfast Icpeac. So important papers are sometimes in conference proceedings to find. And the lifetime there was measured with a conical trap very accurately, and 359 microseconds. This is an eternity for such a small ion. So this lives quite long. Electron affinity is 77 millieV for helium metastable, so also reasonably high, and thus this anion now can be investigated. Let's look at it from the theory side. This is helium plus 1s electron only. This is helium neutral. It's a little bit larger because the 2 electrons are, one is shielding the other, the core a little bit, the nucleus. And when we have helium plus, you see that the 1s electron is actually exactly the same as here in the helium, and the 2s electron doesn't disturb it really. It's basically a cation with 1 electron further out and loosely attached. And the helium minus, it's the 1s electron, the 2s electron, which is disturbed by the 2p electron and getting into an elliptical shape. For the dimer, very similar. It's a helium-2 plus core with 2 loosely bound electrons. Now, in order to have a stability which is so long-lived, all the spins have to be aligned. So they are all quartet states, and this makes them this surprisingly long lifetime. In bulk helium, people measured since the 50s mobility of ions, cations, and also negatively charged species as here. This is a recent paper 2 years back when they had a pulsed discharge here, a corona discharge in front of a superfluid helium container, and they dragged negatively charged species through this liquid and measured the arrival time. And there was a species which is very dominant. They called it N, the normal carriers, and they have here something which they call fast or sometimes exotic carrier, because the experts in this field still didn't know, even at that time, what is the nature of these anions. So what negatively charged species is responsible for being so much faster than the electron bubble? So the electron bubble is really inert. It's huge. I told you already, 17 angstroms in size. So this is very immobile, but there is something which has higher mobility. They even discussed in some papers, it could be helium minus, it could be helium-2 minus, or it could be double electron bubbles. But they were never clear, and they couldn't measure it, because this is only a drift ion mobility experiment. It never gives you the answer, what is the mass of the anion or the negatively charged species. In the Göttingen group, anion efficiency curve were measured for heavy anions. This is the huge droplets and how you can form them. At about 2 eV, you have a narrow resonance. Then there is a resonance at 22 eV, followed by a peak at 23 and 26. At 44 and at 66 eV, there is a kind of a repetition of this structure. The explanation was, here we have an electron bubble. The electron requires about 1.15 eV in order to go into the conduction band of helium, to penetrate into the droplet, and then it has to form the bubble, which costs another little bit of energy, which is leading to this peak. At this energy, we have high enough energy to form a metastable helium, and the decelerated electron, which is released or scattered inelastically from the helium atom with which it's colliding, has an energy just perfectly fine for forming again a bubble. So this was all explained by electron bubbles. 10 years later, our experiments in Innsbruck, the first one who ever achieved anions from doped helium clusters, was measuring here D2O, so the dimer of heavy water, and it's formed exactly at the same positions. So at that time, we also thought this is the electron bubble. This is an electron which has scattered and lost most of its energy, and again forming a bubble and attaching. Recent measurements done by Stefan Denifl and his student Elias showed that this is extremely narrow, this feature of the water. And with the same resolution, it would be now very, very beneficial to measure also these states up here. Probably we could then identify the electronic levels that are responsible for forming these anions. Now let's look what helium minus can say about it. This is the same spectrum, the big droplets from Göttingen, and this is helium minus that we measured. Look at this mass spectrum. Helium minus is by far the most dominant anion that is formed. It's a huge yield. We hardly ever get so much anion yield in our experiment. So it has to be a highly efficient mechanism that generates helium anions. And the electron energy dependence here is mimicking perfectly the curves of the heavy droplets. So in our opinion, and Peter Tönnies was also co-author on this paper, we were very sure that helium anions are in fact here the ionic core of these heavy droplets at these energies. The mechanism that is forming helium minus is the following. A metastable helium is formed by collision with an electron. It forms also a kind of a bubble state. The electron is decelerated and forms a huge electron bubble, but this one is immobile and it polarizes the surrounding helium. Helium metastable is about 200 times larger in polarizability than ground state helium. So the two inevitably attract each other and they come together, and it's energetically favorable to end up in this state. So helium minus is formed extremely efficiently. Let's look at the closer look at this electron energy dependence, at this anion efficiency curve. We can fit the curve of helium minus with 3 Gaussians. We have one peak at 22, we have one at 23, and one at 26. These are exactly the numbers that you heard already. For the helium-2 minus, apparently the first peak is missing, and it's clear it has to be missing because When we remember this ionization of helium, the 1s, 2s state has a little repulsive barrier. And so we cannot form a dimer in this state. We have to go into the 2p state, and the 2p state is just 1 eV higher. So this is just the right energy for having 1s, 2p2. This is a different anion. This is in a different state than this one, or even this one. In this case, we are already beyond ionization energy, and what we expect to have here is basically 1 helium plus that is carrying 2 Rydberg electrons with huge bubbles. And that also makes these ions probably with lower mobility, as we will see. And this is the measurement of Göttingen, exactly the same curves for the big droplets. Now, in order to form helium minus in the 22 eV state, we can go to very low droplet size, about 40,000, and we can see this peak nicely, but all the bigger ones are missing. So the high energy resonances cannot exist. When we go to very low temperatures, we have huge droplets. Only then we see the 26 eV contribution quite clearly. So apparently you need bigger droplets for the bigger excited states. And they call them bigger excited, not higher excited, because the shape or the orbitals are simply higher, and the bubble which is formed has to be larger. We also see this indirectly by the response of these different helium anions to dopants. We put here SF6 into our droplet, and the 22 eV resonance decays here by 2 orders of magnitude, whereas the 26 eV resonance only goes down by an order of magnitude. So it's a very different response to impurities, which we attribute to different mobility, and thereby I think we have the explanation for the bulk helium community that the exotic fast carriers are nothing else than different electronically excited helium states. This is summing up this pressure dependence, and you see that the helium minus decays exponentially with increasing the SF6 pressure. And at the same time, the helium dimer almost is unaffected. Strange. How can that be? And this exponential decay fits perfectly the Poissonian distribution, the probability to have 0 SF6 in our droplet. Calculations by Stefan Huber and Andreas Mauracher give a nice explanation why helium-2 minus is not affected by the presence of impurities. This is the response of helium minus being placed into a liquid helium. It pushes away the helium in a sphere which is around 12 angstroms in diameter. So it forms a bubble, and this costs some energy. In order to push away the helium, it requires some energy. But at the same time, it polarizes the surrounding helium and attracts it. So we have a long-range attraction and the short-range Pauli repulsion, and in total we end up with some energy gain due to the polarization. And this is about 8 times higher than the energy cost to form the bubble. For a dimer, in contrary, we have a much bigger peanut-shaped bubble, and the helium is only attracted here and here around this ring. So this is circular in shape, so you can rotate it. And there, the energy cost is about 3 times higher than the gain by polarizing this little bit of helium. So this is heliophobic. And that's exactly the reason. So this helium minus is immobile due to the huge bubble, and it goes to the surface. It doesn't seek an impurity inside, whereas helium minus, as a heliophilic species, is very mobile, and it can find impurities inside. The explanation now for this curve, the hump that we saw on the helium plus at low electron energies. Let's compare it to helium minus, and you immediately see this is the same process. Somehow helium minus plays a role in the formation of this resonance at 22 eV that we see here now in the cation. And apparently 2 electrons are hitting it. We saw this with the current dependence. So we need 2 electrons. One is forming the helium minus, and the second one is a helium metastable, which is nothing else than an impurity for helium minus. So they seek each other, combine, and with 40 eV we can ionize and form helium plus. And this is the last example, in my opinion, the most exciting one. This is a cluster distribution of C60 measured by heavily doping big droplets with fullerenes. It's negatively charged ions, and you see a lot of singly charged species This is monomer, dimer, trimer, and so on. The neighboring peak here is a little bit water impurity, but it doesn't bother us too much. But there are peaks that appear only here between 2 and 3, 3 and 4, and so on, just in the middle of the two singly charged species. And this is a strong indication for dianions. When we look with good mass resolution to the dianions, this is the isotopic pattern of C70 dimer. This is the isotopic pattern of C75- as it should be, and it matches perfectly the profile that we measure. So it's a clear indication that we form dianions. It's extremely much signal. It's very abundant, so the process has to be efficient. And when we look at the electron energy dependence for the formation of the dianion in red, we see that it has this peculiar shape of a steep onset and some 3 peaks that we already know very well, 22, 23, 26. So it's nothing else than the helium minus. So helium anions have not only the possibility to charge exchange, giving the one loosely bound electron to a dopant, they can even transfer both electrons. And this is shown here, finally, in this animation. I think I'm a little bit out of time. So here we have helium minus being formed. First, helium metastable, electron bubble. They polarize each other, they come together, recombine, form this very mobile and small anion. It is attracted by charge-induced dipole interaction to the dopant. It transfers both electrons in one process, and it forms a dimer cation, which is recoiling from the dianion being formed. So this is a short summary. Basically, what you should take home message is that in helium droplets or in bulk helium, helium anions can be formed very easily, very efficiently by simply exciting one helium metastable with an electron. Then inevitably we will end up in this helium minus, which is doing a lot of chemistry by its low electron affinity, by its high internal energy, and by the possibility of even transferring 2 charges to a dopant. With this, I want to thank you all very much for your attention, and thanks.